All right, welcome back everyone. We're going to shift gears now and move into our next topic of masonry. This is Division 4 from the Master Format, corresponds as usual to Book Chapter 4 for those who are reading along. Like our other materials, this is going to be broken into multiple parts. The masonry we're going to cover over 3 parts. We have part 1, which this video is about, and it'll cover properties of mortar and grout, the reinforcement of our masonry structures, and also some accessories with masonry construction. Part 2 will be the manufacturing and properties of clay masonry units and concrete masonry units, otherwise known as CMUs, or you might know them as cinder blocks. And the third and final part will discuss the design and construction of the masonry walls, other masonry applications, stonework, glass, things like that. And you can see the corresponding book sections for each one of these. So let's start off by talking about what we mean when we even say masonry. Well, masonry is basically some kind of block, like a clay masonry unit or a concrete masonry unit, or a stone, like a large stone, right? With some sort of gluing mechanism between it, which here I'm calling it a plastic mortar or grout, which will harden into a solid structure. So history of masonry goes way, way, way back, thousands of years. One of the oldest building materials. We see the Colosseum here with the Romans. We see the pyramids. What is this? The Incas maybe? But regardless, the Romans discovered this idea of the cementatious material, the part that's sticking these blocks together, when they were burning and grinding at some volcanic rock. And so that's what their clue was. Of course, we've come a long way since then, but this is definitely a very historic building block. As with all of our other topics, we should hit on the sustainability of masonry. So if we look at these clay masonry units, according to the American Institute of Architects, we have the lowest embodied energy per pound of all of our cladding materials. Cladding is going on the outside of our structures, right? Our fascia or whatever. So what that means is embodied energy per pound means the total amount of energy to produce our product, to place our product, is lower than any of the other cladding materials. Clay and shale are the primary materials needed to produce one of these clay masonry units, and they're very abundant in the Earth's crust. So it's something that, yes, we are mining it, but it's so abundant it's not really a consideration as far as sustainability. It can be recycled. Our bricks can be ground into this thing called grog, and then grog can be recycled into new bricks. Bricks are also reusable and can be sought after to look for a certain look, right? This is an example from where I was before in Athens, Ohio, at Ohio University. This is the Athens block, and there was a high demand for getting the actual bricks that say Athens block on there, which were manufactured in a facility not too far away from Athens that is no longer there, but these blocks were used to do the main streets, the walkways through campus, in various other locations around Athens, Ohio. And so it's this architectural appeal, right? This aesthetics that looks so cool with all the brick roads and everything else. And then people want this for their own uses as well. They're also far less energy production than steel or concrete. So we talked about the energy needed for both of these with all the smelting and everything. And we actually are lower with our clay masonry unit. However, when we talk about concrete masonry unit, CMU or cinder block, when we talk about those, that is made out of concrete. So we actually have the same considerations as concrete, where we do have a little bit more of a pollutive process, right? However, these are easier to recycle at the end of the life. So let's move on to the components used in masonry building. So the components, we have what I'm calling a binder, which is either the mortar or the grout. And the difference between mortar and grout you should definitely be familiar with. I give you this little thing, mortar sticks and grout fills. So what that means is we have our mortar is in between all of our bricks here, right? So it's the part that is sticking our bricks together. And we also see it here with our CMU wall. But grout, on the other hand, is what's filling up these voids in here, right? So if you've ever looked down one of these CMU walls, they're hollow on the inside. We're filling that with something to give it more of a structural stability. That's the grout. So mortar sticks and grout fills. What are they made out of? Mortar is a combination of the cementatious material, the part that would stick it together, and also fine aggregates. Grout is similar, but grout has a much higher water content, which means that I can pour it into those voids, as I see over there, right? So other than the binding material, I also have the blocks themselves. Blocks could be these clay masonry units or these CMUs, concrete masonry units, or it can be stone. So those are our three primary building blocks that we're building our masonry out of. And last but not least, we have reinforcing and accessories. We'll talk more about those later. But the idea is that, well, we see some reinforcing right here, right? Sticking straight out, going down these voids within this CMU wall. And there could be ties on our brick that are tying back to a structure and things like that. So we'll talk more about reinforcing and accessories in a little bit, but that would be our final component. So let's talk a little bit more about mortar and grout. And like I said, mortar sticks, grout fills. As far as the mortar, where it goes in between, like I said earlier, in between our bricks, creating these little joint lines, right? And that gives a cushion to our units and also gives us a nice bed to set our bricks. You can make them all level, right? So it would compensate for any deficiencies within the brick as well. So what is it actually made out of? If we look at the components of our mortar, the first being the cementatious material, you know, the part that sticks it all together, the part that starts off plastic and fluid and then becomes hard, right? Similar to concrete, its primary component is Portland cement. We also have some lime and some masonry cement in there as well. Our second component would be our aggregate. Now this is clean. We talked about well graded before, different sizes, right? But it's all fine aggregate. This is like sand particles. And then last but not least, we need some water in here. So enough water to give that mixture this workable quality, right? So if you wanted to see what it looks like in the process when we can look at what the consistency of a mortar might look like. I pulled up this short video, see if this will load. So here you can see he's creating a bed to start off his first layer of brick, his first row of brick. And this is called buttering, when he's putting the little extra material on the edge of the brick. And you don't have to know the fine details because you're not going to be bricklayers, but it's always cool to watch these guys work. It's as much an art as it is a science, and there's some speed involved and technique involved. And so look at that, how he smooths it all out to make sure that the mortar is completely covering the brick in question. And you can watch this on your own later, but yeah, I thought it might be nice just to get a little idea. You can see the consistency of the mortar, and you can see how he's layering it up. Of course, with bricks, as you probably know, we're staggering it to get greater strength, right? So let's head back to that PowerPoint. All right, so grout is that part we're filling up within these voids. And so grout refers to several types of construction products depending on the type of material. Yeah, so we can have type 1 grout. So this is used to fill those voids on both reinforced, so we see these reinforcing bars here, and unreinforced, meaning I may not have the bars, but I'm still filling it up with this grout. Same ingredients as the mortar, but now we have it as a pourable consistency. We have a big slump. If you remember the slump test with the slump cone, if I were to do a slump test on this, I have a slump greater than 8, which means that I start off at 12 and it drops down. It's just this little cow patty looking thing at the end, right? And this type of this type of grout can also have aggregate larger than just sand. So you're approaching on concrete type of grout, right? Now, you may have heard grout, or you may have used grout in using ceramic tile, right? And mortar as well. So with ceramic tile, you put the mortar, you have a mortar bed, you put your tile down, you let that set, and then the next day you come back and you are adding this grout. So just like before, you're filling in the voids, right? The mortar sticks, that's what you're sticking your tile down to, and your grout fills these voids. In this case, it's just your joints or your gaps. So for this type of grout, this is called a type 2. It's in filling the joints of unit masonry or stone paving and flooring, and of course that's ceramic tile. So some properties that we look at when we talk about mortar and grout, we have two different types. We have the plastic and the hardened. We did this with concrete as well. So plastic, meaning it's still in its fluid state or semi-fluid state. And the properties we're concerned with is the workability. How easy is it to move it around, spread it, and work it around, right? Water retention. So when I'm putting these bricks on there, brick is a porous material, and it could have the potential of sucking the water out of your mortar, and what that would mean is then you don't have the right water content and you lose your strength. We could look at the flow of our mortar. We'll talk more about that in a little bit, and also the segregation resistance. So we talk about segregation also with concrete, same idea. I don't want the sand to separate from the other materials, right? Versus hardened properties. So after it's set up, then we're looking at its bond strength. How strong is it? How durable is it for wear and tear? What about its compressive strength? So bond strength would be how much force it can withstand for pulling it apart. Compressive strength, if I'm just pushing down on it, how strong is it to keep it from crushing? What about the volume change? So we have heating and cooling. Is it going to change volumetrically with those conditions, right? And finally, the appearance. So what is your final mortar going to look like out here? So looking at more detail for this plastic properties, like I said, the workability is probably one of the key components that we're looking at. And for the workability, we want to make sure that those particles are not going to separate, but we want that mortar to be able to separate or spread easily along our bricks, like we saw with that brick layer a second ago, right? Easily extrudes from joints without dropping or smearing. So you can see when they put that brick down there, it just kind of oozes out a little bit, right? That's extruding out from those joints. Workable grout flows easily without being too soupy, so you're getting that fine consistency. There is no laboratory test to test the workability. Now, for water retention, like I said, the masonry units can suck out that water. It's called bleeding. And that can reduce that bond, like I said earlier. Now, there is a test for this. It's through this idea of flow testing. And once again, we'll see if we can get the YouTube to work. So, and this will walk you through the whole thing. This is an ASTM test. And it's going to be almost similar to what we saw with the slump test, where I'm adding multiple layers. This one I'm doing 2 layers into this jar. And then just like before, where I have my rod and I would rod it 25 times, in this case what I have is another type of device, and I'm tamping it 20 times in each one of those layers. After I get all of this done, I screed off the top, and then I'm going to lift it up just like the slump cone, and now turn this little lever, and it's basically causing the grout to deform out, right? So after 25 times, we see how far it's spread, and we can measure the final diameter. We know the initial diameter, so we have a change in diameter. So there's the change, there's the final diameter with the calipers. And then you can basically just figure out the average of the, then we use our calipers to figure out the average diameter. So here's the equation to find out your total flow. What you have is the average diameter of the mortar minus the inner base diameter of the mold. So what that means is how much did it change? It's your change in diameter divided by your initial diameter, which would be the base diameter. Multiply it times 100 and it gives you a percentage. All right, so getting back to the PowerPoint, that was that water retention test, ASTM test. So that was all of the plastic properties of mortar. Now we can talk about the hardened properties. So what we're concerned with is a bond strength. The bond is, how much the bricks are sticking together afterwards. Of course, it's one of the most important attributes. It is a function of the mortar flow into these void spaces. You can imagine it going into the void spaces and kind of locking into place, right? And it's also related to flow. So once again, you have this flow that can flow into those void spaces. We can look at the durability. So basically, the biggest issue with durability is water penetration. If I have water going into my mortar, it could have some freezing and thawing and in essence, crack out all of my mortar. And then last but not least, my compressive strength. Similar to what concrete is, if I have a wall and it's a structural wall, it's actually pushing down, there's a load, it's pushing directly onto that mortar. And we usually aren't dependent on our mortar for the structural compressive strength, but because if we have too high of a strength of mortar, what can happen is the bricks, as they get hot, they can expand, and if the mortar is too stiff, if the compressive stress strain diagram, if it's too steep, then the brick doesn't have any place to go, and that can cause problems with your bricks. Other hardened properties, we can look at the volume change. This is generally insignificant as long as you've done a decent mix. We can look at water tightness. Like I said before, it's bad to get water into your mortar, but it could get through these small cracks. Typically through vertical joints, and some of that has to do with, if you think about what a brick wall looks like, in profile, what you end up with is like this little indentation, right, for where your mortar is. Well, what that does is if water hits the side of your brick, it basically just runs straight down. It isn't sucked into the mortar. So that's one reason why it says here that it's typically the vertical joints, because on the other side, of course, we don't have this shape and it could get on the sides of it. We can look at the rate of hardening. And you can see this, the speed at which it develops resistance to indentation and crushing, or just how long it takes to fully set up. We can also look at the color, so uniformity of the color. If you have a brick wall, you want the mortar to be the same color throughout, right? And there's a lot of things that can impact it, like that, what the mix consistency is like, or tooling time, atmospheric conditions, if you have any admixtures, things like that. So we have different types of mortar and grout made of different things. We can have a sand lime mortar, and this is more the historical old school one, right? All mortar was sand, lime, and water. Some issues with this is that it hardens at a very slow and variable rate, meaning it's not always consistent either, right? And lime has this low strength, poor durability. It is good for its workability. That's its one big strength. And it's also good because it has high water retention. Now, if we were to look at strictly just a Portland cement, it would harden much quicker and at a consistent rate, and it develops a very high compressive strength. It also has good durability, but the issue with Portland cement is that the workability and the water retention are both very low. So both have their pros and cons. What we can do is we can add them together and we can come up with a Portland cement with lime. It combines those advantages of both and compensates for those disadvantages of both, right? So Portland cement with the lime mortar, or with the lime mortar and grout. And as you can see, it's the most predictable mortar and grout. And then we have our masonry cement mortars, and this is a proprietary, meaning it's a predefined combination of cement, pozzolan slag cement, hydrated lime, convenient to mix up, readily available, produces a good mortar, good workability. Let's take a look more at those masonry cement mortars. So we have different mortar types based on how I'm going to use it, right? And this is a list. We have type M, S, N, and O, and these are listed in order from the highest strength to the lowest strength. So type M mortar, high strength, greater durability than the other types. S is a medium high strength, but where I'm very concerned about bond and lateral strength more than the compressive strength. Type N mortar is a medium high strength, so similar to an S, but now we're talking about more for general use in exposed masonry above grade. And then we have type O, which is low strength, interior non-load bearing masonry. It shouldn't be exterior, at least it shouldn't be exposed to any freezing conditions, right? So let's look at those individually. Type M, the first one with that high strength, has a 2,500 PSI minimum. Because of that high strength, I have less workability than these lower strength ones, the N and the S. It's ideal for this masonry exposed to a lot of freeze and frost action. So because of that, it's ideal for masonry that's going to be below grade or against an earth in a form of a retaining wall. Also ideal for conditions where I'm going to have a high load bearing wall where I'm going to have high compressive forces. Type S mortar, up to 1800 psi minimum. So this has a high resistance to lateral loading, so wind loads and earthquake loads, anything that's pushing it sideways, right? So we have more of that stickiness. Not as much for the compression, but it's okay, but more for that sideways loading. Higher flexural bond, and that's what it means than that N. Type N mortar is medium strength, so we're going down a little bit more, 750 psi minimum. This is your most common mortar, best all-around mortar because it has a good strength and it also has good bonding and workability, right? That's why it's this general purpose. Good for non-load bearing exterior walls. If it's load bearing, you want to go up, you want to have a higher compressive strength like the S or the M. And you can see here we talked about pilasters in a concrete sense, same idea. It's basically like a column inside or along a wall or built into a wall that's carrying, in this case, this beam over here. So there's a high compressive load here, but not too high apparently, otherwise it wouldn't be in this category. Type O mortar is considered a low strength mortar, 350 psi minimum. So now we're talking about non-load bearing interior walls. They're more like structural or non-structural aesthetic type walls, right? Or just a covering. Should not be exposed to freezing, and I can see some issues if I put it in the wrong conditions, right? So as a quick summary, this is our M, S, N, and O. Once again, decreasing strength as I go down. Type M, high strength, high durability, and where would I use this? Where I need a reinforced masonry, a structural wall, also exposure to freeze and frost, right? So this is a below grade type things, foundations. Type S, medium high strength, high bond strength. So now we're talking about more of the sideways loading, where we care about this bond strength more than compressive strength. So exterior load bearing walls in a high wind or seismic loading, anything where I have that sideways loading. Type N, our general use, is good for both interior and exterior. I know this says exterior, but because I suppose if you're only doing interior, you could use type O. Medium high strength, use it in chimneys, parapet walls, exterior walls, or if you have a lot of exposure to the elements. Type O, low strength, non-load bearing walls, or you could use it to repair mortar. So if you had some mortar that had broken out of an existing wall and the wall was still structurally sound, you're not depending on that mortar for the structural strength, you can use that as a repair mortar as well. So this is more of the same, and you can see use, depending on what kind of use, what type you would use, and then from most important to least important. But I feel like we're kind of beating a dead horse at this point. You can take a look at this slide, maybe pause if you want to spend more time, but ideally, you know, what you're looking at is, do I need a strong, like a compressive or a structural? If it has to have great strength, we were talking about our S and M or M and S type. If it doesn't have to be as strong, more general use, S and N. And then, of course, our low strength for just the interior walls, so on and so forth. So when you mix up your mortar and get that good consistency, you should have it all placed. All of your bricks should be laid out using that mortar within 2.5 hours of that mixing. However, if it's hot out, you can imagine the hot weather is sucking the moisture out of it, and it will, in essence, dry out, right? And if that's true, you may need to re-temper it. So re-tempering or re-tempered is the process of adding more water because so much has evaporated out to bring that water content back up, right? Retempering may be limited by code or inspection protocol because it does actually decrease the compressive strength of your mortar. Failure to retemper the material may decrease bond strength, and the mortar may need to be discarded altogether. So let's move on to the reinforcing the ties, the anchors, and the flashing involved here. Reinforcing, we can see that we have this CMU wall, and I have some horizontal reinforcing, and I have some vertical reinforcing. And you can imagine how it's tying everything together, right? Giving that greater rigidity to that structure. And we can use either steel wire or bars. Vertical, we could use steel bars or welded wire mesh. We talked about that before, right? And then we have supplies, structural reinforcing the structure, like I said. So we can also have these anchors and ties. So these are connections to the rest of the structure, right? So I'm tying into, in this case, a CMU wall, right? And I can see these connections here. And every so often, and what that does is now your wall it will be connect the wall and it won't pull away. An older school method, what this is replacing is when you'd have bricks and you'd have like 2 layers of bricks, or you'd have running bonds, something like this, right? So you have more of an alternating to give you that structural strength. Well, another way you can do this is just add these anchors and ties. Could also have this flashing built in. Flashing is to divert the water, so if you get water inside your brick, it'll keep it from settling and getting stuck in this little part, and the flashing will let it run out. Here's a series of different anchors and connectors and things. You can look at these joint reinforcements, so in a way to strengthen our joints and tie it to the existing structure like we were just saying. We have these dovetail anchors, and that means we have a little slot in here that this is fitting into. A whole bunch of different types, right? Here's even more. So strap anchors, rod anchors, dovetail anchors, miscellaneous anchors, expansion anchors. Expansion anchors you're drilling in, and then when you tighten something down, it expands out. These parts are expanding out and creating that connection, right? Special anchors, so just a wide variety of different ways to anchor to this concrete to either hold it in place or attach something to it or whatever you're trying to accomplish, right? So for example, here's a picture of one. This would be a dovetail anchor because I can see that there's a slot in the concrete, and then this looks like it is like a, it gets a little wider and that holds it in place. Then when I put on my next course of brick, this would all be tied in, right? So providing that strength. And this would happen every so many courses up the wall to provide that strength from pulling away from the wall, give it that latitudinal strength. And we can see a couple other anchors along here. This is a short video of how you might want to place these anchors or using. Now these are Posi Ties. It's not like I'm promoting this brand, but we did talk about these steel studs. And if I'm tying exterior brick to these steel studs and I have some insulation, one way that I can do this, let's just zoom, let's just fast forward a little bit, is I can screw in this anchor to the steel stud. This has a little end out of it that then I can tie this triangle wire loop to, and I can see that it can move up and down. The reason I want it to be able to move up and down is because I don't know where the course of brick's going to exactly be. So once we get up to that layer, we can see it sets right in between that course or those 2 courses, holding everything in place. All right, let's head back to this PowerPoint. So, and you can see a variety of other anchors or methods to tie to the existing structure. So here you can see some uses and the material that they be made out of. You should note that they're coated in some way to keep them from degrading, just like a coated rebar, where we need it to be weather resistant. We also see things like we might have plain and deformed. We talked about these before. Plain would be nice smooth versus deformed would have some ridges or something to give it more bite. We can see the ASTM standards for each type, rigid anchors, and so on and so forth. So that's what I have for this one. Hopefully you found that informative as always, and I'll see you all next time. Thanks.